Okay, I'm Gary Lee. I'm a product marketing engineer in the Ethernet products group. I'm going to talk about dynamic device personalization today. Uh, so one of the things that, one of the goals of communication service providers is to try to minimize the cost of their infrastructure as both the bandwidth increases and the number of services they provide increase over time. So some of the things they've been doing in the past, for example, is using standard high volume servers and initially, running complete network functions on a bare metal server, and then moving to a more virtualized environment over time where they can run multiple virtual network functions on a high volume server. And what they're moving to now is to more kind of cloudify, I guess you'd say, their services into cloud data centers. So that gives them kind of more economics of scale and so forth. So running both virtual network functions, in some case containers, and moving to things like running these services on more microservices and so forth. So one of the things that's important here, of course, is that if you're using standard high volume servers, they also want to use standard high volume network interface cards. And one of the things that we're going to talk about here today is the fact that with our Columbiaville NICs and Fortville NICs, we can actually improve the performance of these virtual network functions running on these standard high volume servers. So DDP, dynamic device personalization, this is kind of a high-level view of what it does. So it's really the ability to move frame classification from the host into the network adapter. So if you didn't have that classification, for example, if a frame comes into the adapter that can't be classified, maybe it's one of the more advanced protocols, new tunneling protocol or such. If it comes into the adapter doesn't know what it is. It has to go to a default queue sent over to the host. The host has to run the frame classification to determine which virtual network function this frame should go to. And by running that frame classification on the adapter, we can reduce latency, provide higher throughput, and also improve the efficiency by reducing CPU host overhead. So there's different protocols. The default we call default DDP package for Columbiaville supports standard protocols that are widely used in the broad market. So these are fairly stable protocols that typically NICs need to support. But where we're setting ourselves apart here a bit is we're providing these enhanced protocols in what we call an enhanced DDP packages, and they have additional protocols, and they can right now, most of the target for these protocol is in the comms market for communication service providers. We do have applications. In some cases, we will do custom protocols for cloud service providers who may have like proprietary headers in their data centers. The charts on the right, well, you can see on top that DDP is currently available in our 700 and 800 series adapters. The charts on the right, the top one is a Metalastic white paper, which I have a link to at the end. And they use DDP in the 700 series. And by enabling DDP, we're able to improve throughput by a factor of 2 to 3 compared to when DDP was not enabled. The chart on the bottom is actually a South Korea Telecom test case. So they have a white paper as well. And I'll talk more about their application in this slide deck. What they're doing is classifying packets as high priority and lower priority, and the high priority packets get dedicated queues and so forth, and so they see much lower latency for the high priority traffic than the low priority traffic, and I'll explain more on what that looks like on an upcoming slide. So the reason for DDP is the changing network landscape. So we have as I mentioned, there's a lot of kind of what you call standard protocols, maybe in the enterprise, where most modern NICs will support these types of protocols, tunneling protocols for virtualized networks and data centers and so forth. The service providers, communication service providers, also have a lot of tunneling type protocols with different VLAN tags and so forth. Where it gets interesting is in the 5G market. We're working closely with our partners at Intel. We have a network products group at Intel that focuses a lot on the network segment, especially 5G. And so we're working closely with them. And there's a lot of protocols emerging that they're working with us to enable with our DDP technology. So you can see there's a lot of tunneling type protocols in the network edge. And then finally, security, things like IPsec and so forth. We can support matching on headers, IPsec headers, and so forth as well. So this is a simplified view of the frame processing pipeline of the 800 series. So probably most people are familiar with how a pipeline like this works, but the packet parser block really is what examines the incoming frames and extracts certain headers to match on those incoming frames. And I like to think of the parser block, it's a parse graph that it's kind of like an if-then type parse graph that, if this Ethernet frame type, then skip this many header bytes or bits and look at this header field. If this header field has this information, and then you may want to skip more bytes to extract more header fields. So it basically is where the frames are identified and classified, and that's where the DDP package really resides in the parser block. The switch block, identifies packet destinations. Is it a loopback or is it going, forwarded to the ACL block, for example? Access control lists. That's where you can do things like look at frame header fields and decide to perform action. It's kind of a match action type block, so it can do things like drop a packet, count a packet, and so forth. And then we have classification filters. So you're probably familiar with flow director, which is, well, let me start with RSS. RSS is really a way to use hash-based mechanisms to send packets to cores and kind of a hash type algorithm. Flow director is a little bit more stateful. It looks at frames and identifies, let's say, which frame type, which flow, what core a flow came from, and then when it receives a flow, it'll put it back to that same core, so you get better performance. And then, as Brian talked about earlier, there's application device queues, which can not only, don't associate frames with cores or flows with cores, but actually associate them with applications running on the host. So these are the kind of forwarding that we can use. So we can match with the DDP. We can extract the right header fields with the DDP, and we can match and send it to the correct queues that are associated with RSS flow director or ADQ. So this shows a kind of a pictorial view of what might happen in a host with a NIC with and without DDP. So the top one would be without DDP, where a frame would come in. You may have to have cores with DPDK running, efficiently moving those frames from the NIC into the host. And then you may have cores that do the frame classification. They examine the frame header fields and decide what processing core these frames need to be moved to. So you then have to send from the distributor cores to the processing cores, and then finally on the transmit side. And that's all software-based, type flow movement and frame processing. With DDP enabled, the receive side, of course, can do more direct queuing directly to the processing core. So you get, much more efficiency that way, and reduces the core count, which overall can reduce the TCO in cloud or communication service provider data centers, for example. The 700 series, this shows kind of a simplified view of the 700 series and what types of DDP capability we have. So we have these NVM image protocols, which are more standard protocols, as I mentioned earlier. So when the NIC boots up, it loads these protocols into the parser block from the NVM image. And so these protocols are loaded, and then on top of that, you can actually load one of the more advanced protocols, one or maybe two at most. So you can see there's a list of more advanced protocols that can be loaded in addition to these NVM image protocols. And on the right side, you can see the protocols available currently today for the 700 series, and they're publicly downloadable. These are, there's no license fee or anything of that nature associated with these. So with these protocols, you can see the segment use case. There's a lot of wireless cable modem termination system, wireline, and so forth. So a lot of communication type applications can take advantage of DDP using these downloadable protocols. So the 800 series is a bit different. We've decided to change things a little bit differently here. So instead of adding protocols on top of other protocols in the parser block, we actually download packages. So we have three types of packages, as you can see here. There's the NVM image package, which is, again, more common protocols. Then a superset of that, so the NVM image protocols plus the default protocols would be downloaded with the driver. So our driver OS vendor would come in and provide that package when the driver boots, it will actually load that default package into the parser block. And then we have these enhanced DDP packages, which can be loaded by the driver. It can be loaded through DPDK driver, for example, or standard Linux driver. These enhanced these enhanced DDP packages include not just a single additional protocol or one or two protocols like on the 700 series, but can include multiple protocols. So you can see on the right side, we have our first DDP package that we've offered for the 800 series. We call it a comms package. So that has 5 different protocols available for the communication service providers to use to enhance the performance of their NFV workloads. So one of the advantages of dividing up the protocols into these multiple packages is that, for example, you can, like an OEM, for example, could qualify a NIC hardware in their server using the NVM image protocols. And if let's say there was a change to the default protocol for some reason, or the enhanced protocols, it would not affect that hardware kind of certification, so to speak. And then additionally, when an OS vendor ships a driver, they have to certify that driver, and by certifying the default plus the NVM image protocols into a default package, if something were to change in the future, let's say we offer more packages, different enhanced packages, that driver certification is still valid. So that makes it a lot easier. That's one of the reasons we have divided it up into these package types. So we have this comms package today. We have a roadmap we're evaluating right now. There's about, I think as of yesterday, there was like 10 additional protocols, or 6 on top of some we already have, but total of 10 protocols. We're looking at providing that as 1 or 2 additional packages. So we're evaluating that, but expect over time we'll have more packages for wireless access applications or radio applications and so forth. So again, we've been working closely with our network products group, who has very good close relations with some of the key either the TEMs or the communication service providers out there. So there's a white paper on the left. It uses the 700 series. It's a ZTE white paper, and it shows how performance can improve using dynamic device personalization. And then the one on the right is actually the 800 series. South Korea Telecom has a public white paper out there where this is where I showed the graph earlier, where they're classifying traffic for 5G applications as either high priority or lower priority. And then with the higher priority traffic, they can see a reduction in round trip latency of 78% and a reduction in jitter of about 88%. So this is especially when you want to process high priority traffic in a comms application, this is very important. So this is just kind of a high level view of what they've done and what the white paper is all about. So this is a 5G UPF application using priorities based on 5G packet classification. So it has kind of 3 pieces to it. The DDP part, which is kind of one of the key piece here, is flow classification. So we look at a couple of priority fields. One is a QFI field and a GETP header, and one is the DSCP field and the IP header. And they use that to classify the frames as either high priority or lower priority. So the packet steering, then, of course, they use RSS in this case. You could use flow director. You could even use other techniques, but currently they're using RSS, and they send the frames to these queues, which then the worker cores, which is the final piece, they use scheduling logic to pull the packets from these queues based on priority, based on a weighted priority, and then process the packets. This is a good application using RSS. We're also working in the future. We're expecting maybe we could use something like ADQ as well. So not sending necessarily packets to cores, but maybe sending packets to applications running on those cores. So we're evaluating that as kind of the next step. So as a summary of dynamic device personalization, it uses our existing hardware, 700 series, 800 series devices. With the 800 series, we've added the additional capability, what we call enhanced DDP packages, which include multiple protocols. And as you've seen earlier, there's a lot of different adapter types available for these products, a lot of different port speeds, form factors, number of ports, especially in the comms applications. That's where they're very interested in, let's say, quad port devices. And in the future, we're even looking at 8-port devices as well. So this is something that we can offer, which is a nice feature, is multiple port capability. And then it also, as we said, improves network efficiency by reduces CPU utilization, so it can improve packet per second processing rates. You've seen reducing process latency and latency variation and CPU utilization efficiency. And again, just repeating these charts from earlier on of latency and throughput, showing the improvements that we talked about earlier. And then finally, dynamic device personalization resources. If you go to intel.com/Ethernet, you can see some of these white papers. We're constantly expanding the list of information on DDP. So there's Intel Developer Zone article, which is shown on the left here, which is a more in-depth technical deep dive into deep DPDK. Currently, we have a page for the 700 series. We're in the process of working a new page for the 800 series. NetElastic white paper, which I mentioned earlier, the ZTE white paper, those are both around the 700 series. And then for the 800 series, we have the South Korea Telecom white paper and there's an ASTRI white paper, which also shows user plane function performance improvement. And then finally, there's a YouTube video Brian Johnson put together on DPDK in March of 2018. So although that's a couple of years ago, but it's still relevant. It shows a lot of information on dynamic device personalization if you're interested. So to summarize the 800 series, we've talked about these. So Brian mentioned ADQ, which is advanced traffic steering capability. It's really a way to assign applications to and associate them with queues in the NIC hardware, such that you get much more predictable response time, lower latency variation, and it accelerates network performance while meeting service level agreements. And then Fred and Dave talked about NVMe over Fabric. We support multiple transports, as we mentioned, IWARP, Rocky, and TCP. And so the real benefit here is that we can support all of the Ethernet-based storage protocols and provide the customer with a flexible choice of how they want to implement their storage requirements and in the scale to both scaling and in performance. So they have high performance storage requirements. We can help improve that. And then finally, DDP, we talked about this, enabling segment-specific protocol definitions to improve packet processing efficiency. And one of the things I probably failed to mention, we have on-demand support of DDP, which is nice. You can actually load, let's say, new enhanced protocols in there at runtime. So this is the dynamic part of dynamic device personalization. and it reduces CPU overhead while improving throughput and reducing latency.